Very good. So, okay, let's begin. So today is my great pleasure to have Dr. Kevin Church. Today we will have a very unusual talk because now it's midnight in Canada, and I am very honored that he accepted our invitation. And today he's going to, and also he's now working at the bank, Canadian Imperial Bank of Commerce, but still he's very insisting in keeping research, and I admire this very much. And today he is going to teach us a very new topic in Taiwan about computer assisted proof. And the title is very amazing, appearing, right? We are very curious how unreasonable of computer assisted proof is. So let's welcome him.
Thank you so much for the kind introduction, Jawan. So, yes, as you said, yes, I'm no longer strictly speaking a mathematician. I work at a day job, 9 to 5, at a systemically important Canadian bank. But of course, still spend a couple hours a day doing mathematics research, and have a few projects still very much on the go. And was invited to give this talk in the scope of computer-assisted proofs, and I thought it might be nice to talk about some of maybe the misconceptions around computer-assisted proofs. Sometimes these ideas can appear to be like almost magical black boxes with how, one, effective they are, and two, sometimes how impenetrable reading a proof can be. So with that in mind, I thought might be a nice way to just kind of give an introduction and explain how exactly I got into computer-assisted proofs a few years ago, and how my thought process around what these things are has kind of evolved. So to just and also just to give a good example of what a large result that has been proven using a computer-assisted proof fairly recently. So there is this fairly old conjecture called Wright's conjecture, which was just proven in 2018 by Jan van Vandenberg and Jonathan Jacquet. It concerns this delay differential equation called Wright's equation in this first row up here. And as this is this is a webinar on evolutionary dynamics. Maybe some of you know of mathematical ecology. There's this delayed logistic equation, or sometimes called Hutchinson's equation, which is in fact equivalent to Wright's equation by a very simple change of variables. So there is this Wright's conjecture states that for Wright's equation, for the parameter alpha appearing right here, if alpha is between 0 and pi over 2, the conjecture states that the origin is the global attractor on minus infinity to plus infinity. And there is a very large history of work that has gone into proving this theorem, and it was ultimately settled in 2018, and the proof is indeed computer assisted. There's a lot of analysis that goes into this, which is not done on the computer. It's all by hand, very much classical analysis techniques, but the final piece of the puzzle is computer assisted. Slightly more impressive in some ways, proven in 2019 by one of the same authors, Jonathan Jacquet, who I believe is currently at Boston University, I think. Which states that if alpha is bigger than pi over 2, then Wright's equation has what is called a unique slowly oscillating periodic solution. Exactly one periodic solution of this very, very specific type. This was once again proven in 2019, and the proof is computer-assisted once again. And I was reading about these two results in maybe 2015. I was completing a PhD. I was coming from much more sort of classical nonlinear analysis, center manifolds, nonlinear dynamics, stability, in the context of delay differential equations with impulses, so discontinuous, somewhat weird semiflows. And I was maybe looking to branch out, and I saw these results, and these seemed like kind of interesting, kind of surprising. And I looked at the first those papers from 2018, 2019, and I didn't understand anything. Nothing made any sense. So I went a bit further back, and this was one result by Jean-Philippe Lessard in 2010, which is a very big piece of that proof of Wright's conjecture. And it essentially connects what was known about a Hopf bifurcation in Wright's equation, so that delay differential equation from before, with a global branch of periodic orbits. And it's a very strange result if you do not do anything with computer-assisted proofs, or if you maybe do not necessarily always really get your hands on obscure numerical constants that might appear in the construction of a proof. Because the setup is we have some small number epsilon, and Jean-Philippe has proven that for the parameter between pi over 2 plus a tiny epsilon and 2.3, the branch of periodic orbits that comes out of the Hopf bifurcation in Wright's equation does not have any folds. So, which means that in some sense, if you increase the parameter alpha monotonically, then there's a nice one-to-one correspondence between the parameter and the periodic orbit. And I looked at the proof as much as I could, and once again, it was extremely confusing. You know, I feel as though when you go and you try to learn about new mathematics, you go through a few different stages. So you'll forgive me, I'm making a bit of a joke here, but in much this way as there's this 7 stages of grief, there's also 7 stages of mathematics appreciation, and the very first one is of course wonder. We look at this result and they say, wow, that's incredibly impressive, and I have no idea how I would prove that myself. And apparently there's this new mathematics that does it. In this case, it's called computer-assisted proof. And then you try to learn about it, and you're immediately very confused. This reveals your own, shortcomings, your lack of understanding of perhaps some fundamental topics. In my case, a big part of this, beyond just a bunch of really technical code, which is important for the proof, but is actually almost a side effect, was that in my case, I spent my entire 4 years of PhD doing very little Fourier analysis, and a big part of the proof is Fourier analysis in the case of this Wright's conjecture. So after confusion, I would say there's the irate skepticism phase in which you cannot believe that it works and are almost irritated that it does seem to work. And again, this is an example of, in my case, probably my own insecurity. I don't understand it. How can somebody else get this? And that's just, we oftentimes, when we're so experienced with mathematics, we sometimes forget that there are sometimes entirely new techniques that are so different from what we do that, in fact, it's normal to not understand them. And then we try again. We spend a bit more time being confused, and then we just decide to learn about these methods outright and apply them to our own problems, right? So in my case, I was still working in delayed differential equations, impulsive delayed differential equations, and I worked with Jean-Philippe Lessard for a couple of years, starting in 2019. I applied these ideas to spectral methods for impulsive delayed differential equations, learned all the basics, and then the first time you have a really successful project, you move into what I call the zealotry phase, in which you're convinced that this is the new way of doing everything, right? So we learn that we learn the effectiveness of some new piece of mathematics, some new theory, and that generally results in you doing a bunch of work in that area and proclaiming to everybody that this is very cool stuff and is the future. At least that's how it seems in this field.
But Kevin,
yeah,
I have a,
yeah.
I also want to share my personal experience. When I learned this success of computer-assisted proof, I also had a stage of depression because I have already learned so many years about nonlinear dynamics, but my theoretical tools cannot prove this, but this computer-assisted proof all. So I should have learned this long time ago. So this is a depression.
Yes, I suppose one of those confusion phases might be the depression phase. That's certainly possible. Yeah. Yeah, your own results may vary. In my case, the irate skepticism part was more anger, but that was very short-lived. So
But then you decide to work on this, but maybe some other people still insist on doing theoretical stuff. Do you know?
Oh, yeah.
Do you know why? Why these
Um,
two?
Wow, I can't comment on that too much. I mean,
Yeah, yeah, yeah.
there are plenty of things that computer assisted proofs cannot help you with. There are plenty of results that, well, for reasons that we'll talk about later,
Yes.
computer assisted proofs will not work for. Um,
Uh-huh.
but yes, yeah, your
But we can
results may
discuss
vary.
this later.
We'll talk.
Okay. Yeah, yeah.
Absolutely, we'll talk about that later. Yeah.
Very good, very good.
Um, so yes, we get into this sort of very excited phase when which zealotry I call it. And maybe if you do this for a few years, I don't entirely know. I'm not at this stage myself, but maybe you eventually get to the point of bored satisfaction where you become complacent, and then we'll emphasize this a little bit later. But in my opinion, mathematics appreciation is a cycle. Eventually, somebody shows you something new again, and then it starts all over, and that's why this job can be interesting. Um, but jokes aside, let's talk about some applications of computer-assisted proofs in dynamics. Really early ones, some that you might be familiar with, some maybe that you are not. So going really far back, 1982, Lanford proved the universality of the Feigenbaum constants in discrete time maps. There was a small omission in some sense in the proof, which was corrected in 1982 by Eggman and Wittwer. So first, computer-assisted proof in dynamics is basically mid to late 80s. Obviously, things are very different now. Methods have changed a lot, but if you're going by the history, that's how far back it goes. The last in this sort of block here, I would say, is proving that the Lorentz attractor exists, specifically that the Lorentz equations at the classical parameters supports a strange attractor. This was proven in 1999 by Warwick Tucker, which settles, I guess, fully settles. It's is it Hilbert's 14th or one of Smale's problems? I can't remember which one, but again, one of a big problem in mathematics at the time. And then in the between, there's some results by Meshekov and Wozek about chaos in the Lorentz system, but not necessarily the strange attractor. That was 1995. If we're strictly speaking, talking about the strange attractor, it's 1999 with Warwick Tucker. Then there's some work by Zygninsky on the Rossler equations and the Hanon maps in the 90s as well. Moving to a bit more modern time, quote unquote. Again, I'm not talking exhaustive results here, just highlighting a few kind of big papers and sort of current ongoing projects. There are the proofs of the Jones and Wrights conjectures, which in terms of, settling very old problems in computer-assisted proof, they're very self-contained and they're very, if you look at them, it's sort of clear where you can see where the computer-assisted proofs are coming into play. There's actually a lot of work in celestial mechanics that makes use of computer-assisted proofs. I'll just mention this one paper in 2019 by Burgos Garcia Lasar and James on circular restricted four-body problem. And there's currently a lot of work being done to try to actually prove that the Mackey-Glass equations of delayed differential equations are themselves also chaotic. So there's one student of Jean-Philippe Lessard, my old advisor at McGill, who's trying to do this by finding a horseshoe connected, like a topological horseshoe connected to an unstable periodic orbit. And at the same time, there's a group in Poland that's also trying to do similar things using entirely different techniques. So there's a bit of a race going on right now, if you will. A few people are trying to do this at the same time. And then there's a group of researchers, mostly in Japan, that are currently studying blow-up of solutions in ODEs from the lens of computer-assisted proof with a sort of compactification of phase space. And I think the goal is eventually to try to apply this to PDEs. So that's a little bit of what's going on right now. Of course, I'm not being exhaustive here at all. I'm not talking about partial differential equations at all, because it's not really my area of expertise, and I'm not super familiar with a lot of the work that's going on there, but it is also very active. So with that in mind, we've talked about a lot about applications of computer-assisted proofs, and I feel like it's probably a good idea to talk about what exactly is a computer-assisted proof, because this is there's a lot of contention around this and, whether you should even trust a computer-assisted proof. So I'm going to paraphrase a description by Alberto Gomez-Serrano from his 2019 paper on really a survey of computer-assisted proof in partial differential equations. And the main idea, or points, which I've highlighted in blue here, are that for the first step, you would perform an analytical reduction of the problem into a possibly large set of open conditions. This emphasizes that in a computer-assisted proof, often the problem that you are trying to solve might not be the problem or the thing that you're going to end up proving in the end with a computer. It might be a transformed problem that's in some way equivalent. There is typically a lot of analysis or, intuition into the problem that informs how the proof should be set up. And that's how it is in mathematics anyway. We don't just take the big result and just prove it and make it work. We often need to, think about it a little while and do something a little bit more methodical to get there. So taking these typically open conditions, we then might have a very, very large list of things to check. We might have an exhaustive list of conditions or inequalities that need to be verified. And the main point of the computer-assisted proof is that this list is too big or too complicated to be checked by hand, even if a human could do it without computer assistance, given enough time, space, graduate students, or pages in the journal, page requirements in the journal. So sometimes a computer-assisted proof, if you were to print all of the output that a computer was doing, all the calculations it was doing, it would take up thousands upon thousands of pages. That's not feasible, but in principle, this could all be done by hand, right? So that's the main point of a computer-assisted proof. It is in principle doable by hand, but we don't because mathematicians are lazy, and we can get the computer to do it better. And with less errors. This is a very important point. Humans make arithmetic mistakes. Computers technically do as well, but much more rarely.
So Kevin, I have a question.
Yeah.
So
yes.
Are you saying that if we cannot do this by hand, then we cannot use computer-assisted proof? Is that correct?
Technically, yes. Technically, everything that you do in a computer-assisted proof can be done by hand.
Okay, interesting.
Yes.
Yeah, thank you.
The limitation only comes down to the amount of calculations. The methodology or the sort of conceptual idea behind a computer-assisted proof compared to an analytical on-paper proof really just comes down to not being afraid of brute force calculations. And I totally understand it. Coming from where I came from during my PhD, more classical analysis, it's a big adjustment recognizing what things are feasible on a computer and which things are not. So it is a big adjustment. Thank you for the question. So to get a handle on how a computer-assisted proof works, I'm going to talk about one sort of setup, which is used by, again, the group that's, mostly, the Dutch group that you mentioned before, my Jean-Philippe's group in McGill, Jason Morales-James's group in Florida Atlantic, which is based on, at its core, Newton's method, which is a very simple thing, which all of us probably at some point at least saw during undergraduate studies. Just a reminder, Newton's method is basically a root finding method. If you have a nonlinear map F, which is continuously differentiable in the neighborhood of some zero, then if you are to start this so-called Newton iteration, which is this map written at the top here, then Newton's method will converge locally to your zero, whatever that happens to be. And the proof is a very standard thing. You definitely do need the continuous differentiability of F, but you can just basically show that the Newton operator, this map right here, is a contraction nearby the zero. The difficulty with it is that in the context of applying this method for a very complicated problem, maybe I don't know, some of the problems we'll show you later, there are some limitations. Two of them are a little bit more subtle, which is that it might be difficult to evaluate your map, f. The derivative might be difficult to evaluate, and for that matter, even more complicated. It might be incredibly difficult to calculate the inverse of the derivative, especially in the context of an infinite dimensional Banach space. It might be incredibly hard to invert the derivative, if you can at all. And then, a bit more importantly to the application, we don't usually know that we have a zero when we start the iteration. We're typically starting with a good initial guess. The way you would teach Newton's method to an undergrad, you start with an initial guess, you run your iteration, Newton's method gets better. The guess that you start with gets refined, and then f at the next iteration is in norm smaller than it was when you started, and it gets better and better. But we don't know that we have a zero nearby. So we might want to know if f of our approximate zero is like in norm 10 to the minus 16, does that mean we have a zero that is 10 to the minus 16 close to it? Maybe there's a 0 10 to the minus 4 close to it, 10 to the minus 7 close to it. How close is it? We don't have any kind of measurement tool that actually tells us this using the lemma as it's stated. So this is the problem with Newton's method if you actually want to do calculation with it, or proofs with it. It's kind of a black box. So to give you an indication of
Kevin,
application.
Sorry, Kevin. Before you proceed, I have a question. So another question is when the derivative is almost zero, like bifurcation. Is this a problem or not?
Absolutely, yes. And that's we'll talk about that a little bit later on, and that's the problem that you and I are currently working on. That's actually one of the reasons.
I see.
That's one of the things that can cause a problem, and that's when you have to think a little bit more.
Yeah, I will keep this in mind. Okay, discuss.
Keep that in mind. Yeah, it's true. That's very important. Yeah.
Thank you.
Yeah. So this is how Newton's method operates, and I do want to emphasize the difficulty of evaluating f. You might think this is just a problem for an infinite dimensional Banach space, but I want to challenge that and give you a finite dimensional example where f is very hard to evaluate. And this is coming from a project that I'm currently working on with my old advisor from McGill and a collaborator in Poland. We're studying neural network controllers designed to control mechanical systems. And one of the sort of benchmark problems in control theory is stabilizing the inverted pendulum. So we have this ODE, basically the nonlinear pendulum with a weird scaling. So you can kind of ignore these constants, the constant 3, the L, the M. Those L and the M are the mass lengths and all these things. There's a 3 here, but this is mostly because we were starting from, we're basically analyzing a network that was developed by other people, and we're just trying to understand how well it works. So you can ignore the constants, but basically we're stabilizing the inverted pendulum, and we have a controller, U, which is going to be basically a neural network. And we're interested in questions like how well this controller behaves. And since we're talking about evaluation of functions, and I claim that this can sometimes be non-trivial, I want to explain how this neural network structure works. And if you don't know anything about feed-forward neural networks, that is totally fine. The main idea in this context here is that this function u of t, it's actually a function of state theta. And the way it works is that for this particular problem, because that's how it's been set up, you take the angle, theta, compute cosine, sine, and the derivative of the angle. Because again, this is a second order ODE, the derivative is available for evaluation. And then we take that information and we compute a affine linear map applied to that vector in R3. We then apply this very standard nonlinearity in neural networks and deep learning. It's called the rectified linear unit. Basically, it's just flat if x is negative, and then it's y equals x if x is positive. We apply that element-wise to everything that has been outputted by the first affine linear map. We apply another affine linear map. We apply another layer of this rectified linear unit apply one more non-linear affine linear map, and then take element-wise, then take the hyperbolic tangent of the output. The reason this is hard to evaluate is that in the structure that we are using, the middle layer F2, the affine linear map is defined by a very, very large matrix. Very large, and of course depends on what you think is very large. In our cases, and in the cases of the papers that we're basing our work off of, the largest layer is 300. So why is this map difficult to evaluate? It is because we end up multiplying very large matrices together. We end up performing slightly weird logic piecewise linear functions at each step, and then composing this operation over a few times. And the question I might want to ask, a preliminary question, which is actually not too hard to answer, is does this controlled system have any steady states? So again, U up here in this very top equation, this is that neural network from before. And just, second order ODEs, theoretically, we're going to have a steady state of this equation if and only if the right-hand side is 0. Now, taking into account that, and just for generality, since our controller script n does use the derivative of theta, which is the angular velocity, we may as well just assign it a symbol and call it omega. So basically, if we have a steady state, then we can define this nonlinear map f of two variables, the angle theta and the angular velocity omega. And a steady state is one for which the f of angle with 0 angular velocity is equal to 0. So this does reduce to a scalar function of one variable mapping real to real. This map is not exactly easy to evaluate. It's not everywhere differentiable, but if you ask a first-year undergrad that's been paying attention in their calculus courses, they can say, well, we can use the intermediate value theorem to sort of prove steady states, because we can just bracket zeros, find somewhere where the f is positive, find somewhere where f is negative, we're good to go. It's fine. So this is trivial, right? Well, let's make it a bit more complicated. So in this study, this robustness study that I'm working on, we're looking not only at steady states, but we're also interested in determining whether the controller is performing the way it should be. And one thing that we're interested in is whether if you simulate this system using forward Euler, whether, for example, there are some weird solutions like periodic orbits. So one thing we can ask is if we, say, look at the step size of the Euler method, whether we have periodic orbits for certain step sizes. And if this is the case, then that basically means that, well, the controller is not performing the way it should. So we're interested in this for other reasons that I won't really get into. But the main point is that if you set up an f of x equal to 0 problem to solve, where the solution of that corresponds to a periodic orbit in this sort of discrete time setting, then the map is much more complicated. So in order to evaluate it, you would have to compose the Euler step map with itself some fixed number of times, because in a discrete time setting, a periodic orbit is one where you have a state, you map forward, then you go somewhere else, and you map somewhere else again, and eventually you come back to where you started. Modulo 2 pi in the angle in this case. This is a fairly difficult map to evaluate now because we have to compose this Euler step with itself m times. Each time we do that, we are doing all of these big matrix operations where at every step we're applying nonlinear, piecewise linear functions that are non-differentiable. And of course, at the end, we have this really, really ugly non-differentiable map, which is piecewise smooth on a few different subdomains of the plane, but we have no idea to really figure out where those are. It's very difficult to figure out, just based on this map representation, where this map is smooth. So how do you apply Newton's method and a computer-assisted proof to this? The map itself is actually very complicated. So here is the main idea, or the main setup that we use for a computer-assisted proof. It's a variation on Newton's method, which makes certain results more explicit. Now, this is probably the most technical slide I'm going to put in this talk, and I'm going to spend a little while here. But the main idea is this. We don't work with the Newton operator anymore. We don't work with x minus the inverse of the derivative of f at x times f of x. We work with something called a Newton-like operator, where the inverse of the derivative is being replaced by some constant operator that we choose. The idea is that this operator a should be an approximate inverse of the derivative at our approximate zero. Now, how we construct that is entirely up to us. For a finite dimensional problem, it's usually just going to be the derivative of our map it's going to be exactly df of our zero, our candidate zero inverted. It's going to be very simple for a finite dimensional problem. For an infinite dimensional problem, we are going to be more clever. I'm not going to talk too much about how to construct these things because depending on the problem, you might use any number of different tricks to make this easier to do, and we can talk about that later if anybody's interested. But conceptually, the main idea of this proof is that if we have a good choice of approximate derivative, a, then first of all, if a is bounded, then this quantity y right here, in some sense, measures the quality of our approximate zero. So this is close to, for example, the argument that if f at our approximate zero is close to zero, then we should hope that it is a good seed for Newton's method. Newton's method would converge, and maybe we have a true zero nearby. The second thing is that we have this bound z of r, which this is probably the more confusing part of this particular version of Newton's method. The idea is that a priori we pose that we think the Newton operator is going to be a contraction on some set. In this case, it's a closed ball centered at our approximate zero x bar with radius r. And it turns out that, just because of how this operator t is constructed, this bound z is essentially a contraction constant on the ball. Now, we'll get to how this actually works out in the computer later on with a specific example. But the idea then is that if we have these two bounds, if this contraction constant is less than 1, and if this bound y is small enough, and this polynomial-like function in R is negative, then in fact our Newton-like operator is contractive. And if our approximate derivative inverse a, if that operator is designed to be injective, then a fixed point of t corresponds to a zero of f. So if we get a contraction, then we automatically have a zero. And I want to bring up one small thing before continuing. This inequality condition right here, I want to go back thinking about a long time ago where I said that a computer-assisted proof typically requires checking conditions that are open. This condition is open in the sense that if I smoothly adjust parameters in the function f, perhaps, then this condition, where this quantity is negative, this will continue to persist if I adjust variables, or if I adjust parameters in f, or I adjust the structure of f in a smooth way. So the main thing is that a computer-assisted proof that uses this Newton-like operator construction is insensitive to parameter variation, at least locally. So that kind of comes to what I was saying before, yeah, where if you have a degenerate situation, you might not be able to use a computer-assisted proof.
Yes, I know. Thank you.
Yeah. So just really quickly, how does this theorem work? It's a very simple three-line proof. It really just amounts to applying the triangle inequality and checking explicitly that T will map this ball into itself and then showing that it is indeed a contraction, provided that inequality condition is satisfied. The kind of neat thing is that having this this inequality involving r times z of r minus 1 plus y being negative, it turns out that this is this is like a one-line check to show that, in fact, actually the contraction is happening. Z is less than 1. And also that there's a self-map condition happening. So it's just a one-line check in some sense after the bounds y and z have been calculated. Okay, so if we go into the computer now and we talk about my horrible neural network problem from before, how do we actually do this in a computer? So for a problem like I have, where my function is piecewise smooth, the way I can ensure that I am working on a part of the domain where my function is differentiable can actually be, in some sense, coded in terms of in the way that, sorry, let me rephrase this. There's a difference between having a nonlinear function and having it implemented in the computer in a special way. So one thing we can do is that we can actually recognize that in my example from before, my map f is a composition of a bunch of piecewise smooth functions. My really important piecewise smooth function that I'm working with is that rectified linear unit. So what I can do is I can implement that function in my programming language. In this case, this is some Julia code that implements this. I can implement it in such a way that it will fail if ever I give it an argument that contains a point where that function is non-differentiable. And in this case, argument can include interval structures. I have not talked about interval arithmetic yet, but interval arithmetic is kind of the key ingredient to make calculations on a computer rigorous. It's a methodology that allows you to keep in rigorously track rounding errors in such a way that if you perform some operation, then the true value of performing those operations will always be contained in the interval that you get at the end. And the key reason that we want to use this is because what we're going to be doing is that all of those bounds that we need to calculate, some of them we're going to be calculating by evaluating them on big intervals. So if we implement all of our functions such that they will only work and return no errors if we're evaluating them on a safe domain where the function is differentiable, then that means that, in fact, these two bounds, this y and this z, can actually be calculated in some sense directly with interval arithmetic, because we can combine some other sort of fancy machinery from automatic differentiation to calculate derivatives of f without actually implementing them. We can evaluate this constant y needed for the computer-assisted proof directly by simply taking our matrix A, applying it to f of x bar, and just taking the norm, doing all the calculations with interval arithmetic, and then taking the so-called supremum. Interval arithmetic produces interval outputs, and in this case, supremum really is just the right-hand side of the right endpoint of the interval. And then this other bound z can be done in much the same way. Instead of having a supremum over a bunch of vectors with norm less than or equal to r, we actually evaluate this function on an interval input. And since we design f to only be able to evaluate safely on an interval that are on a set where it's differentiable, there's no problems. We in fact have a proof automatically that our zero and our entire closed ball is in a part of the domain where in fact our function is C1. So in this case, in this particular case of a finite dimensional problem, it is possible to set things up where you never calculate a derivative yourself. You just implement your function in a safe way and let automatic differentiation handle everything else. Now, I'll talk briefly about a couple of applications of this idea.
So Kevin,
before...
Kevin, hello.
Yes, absolutely.
I have a question. So
yeah.
I know there's an issue about non-differentiable point, but Sometimes maybe we can use sub-differential or pseudo-differential to overcome this. Can you comment on
Yeah.
this?
So the difficulty with using a subdifferential or relying on some kind of weaker form of
Yes.
differentiability is that these notions are not really compatible with Newton's method. Yes, they will still allow for convergence, but the problem is that if you think about it from the perspective of something, I was actually thinking about this a couple of weeks ago, and I came to the conclusion that it doesn't work. And my rationale here was, consider the problem of trying to prove that the function um, f of x equals absolute value of x. Trying to prove that that has a zero without actually knowing what function you're looking at. The difficulty is that if it so happens that you are sitting at a point where your function is not differentiable, then you don't have a zero that is robust under perturbations of your map. If you smooth it in just the right way, then your zero is going to be lost.
Mm-hmm. Yeah, yeah.
And that's why, I mean, there might be a way to set it up so you can do computer-assisted proofs with that, but it's not going to be based on Newton's method.
I see. Thank you.
Because Newton's method can only work at proving isolated, non-degenerate zeros. And in some sense, a zero at a point where your function is not differentiable is itself degenerate. Usually. Yeah?
Okay.
That's my interpretation.
Thank you.
Yeah. It's an interesting question. It's an interesting problem. But yeah, I don't think we can handle it right now.
Okay.
The good news is that again, because that is a degenerate situation, usually if you have a zero in a non-smooth map, it's going to be at a point where that function happens to be smooth, unless you have a function that's nowhere smooth, or you have something really, really pathological. Again, most of the maps we work with when we're trying to apply computer-assisted proof are a little bit more regular. Okay, so we'll just talk a little bit about some applications. I won't mention all of these explicitly, but just putting them up here. I'll put most of the reference. I'll put several references at the end of the paper, but if you're interested in something specific, let me know and I can reference a specific paper for you. So I'll mention in particular, what do I want to mention specifically here? Maybe I'll just mention something that an undergrad worked on while I was at McGill. So I had this student named Clément Fortin. He was coming from physics. He had never done computer-assisted proofs. He would think he was in his second year of undergrad at the time. And he wanted to work with Jean-Philippe. Jean-Philippe was too busy. He asked me if I could work with him. And he was coming from physics, so I looked around for physical problems that he might be interested in. And he ended up proving that there's this in this model of a vibrating billiard. He proved the existence of like 608 isolated periodic orbits using this idea, which I don't know. I thought it was pretty interesting, and he seemed to enjoy it. So it was good. It was good for him. I don't think he does computer-assisted proofs anymore. He's working with the physicists doing something else at McGill. And yes, there are several applications of this idea in finite dimension. Specifically, proving algebraic Hopf bifurcations in a few different scenarios. In particular, proving bifurcations in finite dimensional systems can be done using these methods. But of course, want to talk about infinite dimensional problems. Presumably, these are a little bit more interesting. And so with that, let's move on a little bit. So at least one person in the audience will know why I'm talking about this problem. But again, this is a seminar where some of you might be familiar with predator-prey models. So
Yes.
so yeah, this is familiar to some of you. And so this result we want to prove about this three-dimensional ODE system. There's a theorem that we think is true, which is in progress, and I confess the main reason that it is stalled is because we have one guy on our team that is dead set on doing all of this in Julia and doing this basically with the fastest proof possible. We have a proof that can work. It's just that we're trying to make it better. So the proof is basically done. It's just we're trying to be innovative. So the setup of the result we're trying to prove right here is as follows. So there's this one parameter you can see in this set of ODEs. It's k, and it's underneath the denominator of s right here. And what we want to prove is that so for k between these two numbers, in this case 91 and some decimals to 123 and some decimals, we have a branch of periodic orbits, a continuous branch of periodic orbits that has a few nice properties. So at the left endpoint, the periodic orbit lives in the x2 equal to 0 plane, and all the other variables are positive. At k roughly 123, the periodic orbit lives in the x1 plane, and all the other variables are positive. And in between, this is a biologically meaningful periodic orbit where every variable is positive. So this is what we are trying to prove, and I claim it is a difficult continuation problem, and so let's talk a little bit about that. So once again, one of the guys on our team is an absolutely brilliant programmer. He's a very big fan of the programming language Julia, which I'm now a convert of, and he's also very good at producing in nice-looking graphics. So to give you a picture of what this structure is we're trying to prove, on the left you have a plot of basically the entire continuation of the periodic orbits that we're trying to prove. So again, we have this. So in the red, for example, this corresponds to when k is roughly 93 and we are in the x2 equals 0 plane. When k is roughly 123, we're over here in the x1 equal to 0 plane, and then in between we're in the positive orthant. On the right is just a plot of the period. It's not especially relevant here, but it does help with the color coding a little bit. Now,
Kevin,
yeah.
Do you know the minimal period along the calculation?
Yeah, the minimum period. I mean, I haven't looked at it directly myself recently, but I mean, it's around. Let me guess. Let me try to eyeball it. It's probably 15 and a quarter or something like this.
The right panel, the picture on the right panel is the minimum period.
The picture on the right is the period with respect to k. Yeah.
Oh, interesting.
Yeah. So the period is.
It's decreasing.
Yeah, it's decreasing.
Amazing, really. Okay.
Yeah.
Thank you.
Yeah, you're welcome. Yeah. Yeah. Okay, so yeah, that's basically what we're trying to prove. And I claimed this was a hard problem, and there's a few reasons for why this is a hard problem. So the first is that we have a really large range of parameters to work with, and as you can see, just numerically by looking at pictures, there's a lot of variation of the variables across this range. X2 is ranging from at its maximum around 62 to its minimum 0. This is a really non-local problem. So local methods aren't going to work here unless we somehow manage to stitch things together in a very nice way. And we're basically doing continuation. So, we're not doing this with local methods. But even more problematic is that, so we know from existing work and also just verifying with our own numerical checks that, in fact, when this tube enters those two boundary planes, it actually goes through a bifurcation. So there actually exist periodic orbits in the planes that this tube passes through as k ranges in such a way that, for example, we enter the x2 equals 0 plane or the x1 equal to 1 plane, or x1 equal to 0 plane, I should say. So there's actually a sort of transcritical bifurcation of periodic orbits that happens. And just going back to Newton's method once again to tell you why this is a problem for a computer-assisted proof. Again, I've probably made this more technical than I need to, so I'm going to skip ahead to this slide right here, which is okay. Never mind. I'll talk about this a little bit. My bad. So I think I mentioned it verbally earlier, but to emphasize once again, with a computer-assisted proof, we're allowed, just because of how these conditions that need to be verified being open, we actually get proofs for free of the existence of zeros for maps that are close to F. in a smooth sense. So if we have a map that depends on a parameter, in this case, the parameter k, for instance, if this map depends smoothly on the parameter, then in fact, this proof condition, this inequality, is actually satisfied for a small continuous range of mu. Because again, we're working with a strict inequality, and the fact that f is going to depend smoothly on the parameter. So, in fact, you almost get a proof of continuation for free whenever you do a computer-assisted proof. The problem, which is easy to overcome, is that unless you make it explicit, how much continuation you can do is sort of non-constructive. It's a perturbative result. But what is nice for us is that we can make it constructive. We actually can quantify how far away we can move our parameter around and still have a proof. This is a blessing and a curse. And the curse comes from the fact that this means that it is impossible for us to prove degenerate zeros using this idea. And the reason for that is as follows. Here's a sort of cartoon diagram of maybe a plot of zeros with respect to a parameter. I'm going to call it mu. So for instance, if I want to prove this zero over here, this blue dot, then what I didn't talk about before, that parameter in the proof, computer-assisted proof, the R, is a parameter that basically says how much isolation we have of our zero. And in principle, the largest radius we can have is going to be the distance between one zero and the next closest one. So in this case, it's this distance R max. Now, in principle, when we do a computer-assisted proof, we're never going to be able to actually get a proof at R max. It's just not going to work. We'll have to have something a bit smaller. But if you notice, just looking at this graphically, immediately to the left and right of this blue dot, I should be able to fit a vertical strip that has height slightly smaller than R max, but width, some small little width. I should be able to put a little rectangle around here and not intersect the red curve. So in principle, that's kind of the setup here. Our computer-assisted proof will basically inevitably prove a small segment of the blue curve. But if we're at this intersection point right here, it's impossible to put a rectangle around that intersection point and have it contain only one curve. It'll have to contain both.
Sorry, can you remind me again what blue curve and red curve are?
Oh, okay. Yes, of course. My apologies. I did not say that. So in this figure, it's kind of a cartoon. Basically, the red curve and blue curve are just different branches of zeros of some hypothetical map.
Okay.
It's just a sort of thought experiment. For instance, so the red and blue curve together are kind of like the zero set of a parameter.
Yeah. I see.
Yeah.
And at the intersection point, there's a bifurcation, right?
Exactly. Yeah. It's a transcritical bifurcation of some sort in this case. Yeah.
Okay. Thank you.
Yeah. So yes, the main point is that if we are at this intersection, if we're at this bifurcation point, then there is no rectangle we can place around that intersection that for every mu will contain only one solution or only one point on either curve. And if that doesn't happen, then a computer-assisted proof must fail at that point. So we need to do something to fix this in our ODEs. And this, what I'm going to talk about next, is coming back to what I've said before, which is that sometimes in order to get a computer-assisted proof to work, it is necessary to maybe do some kind of trick or think a little bit outside the box or reformulate the problem in such a way that you don't have this degeneracy that will obstruct the proof. So before I mention that, though, I should just say that for this problem, there is indeed a way to encode periodic orbits as zeros of a map. In this case, we represent periodic orbits as Fourier series, and then we pose our map F on spaces of Fourier coefficients. There's a bit more work to it than just substituting x as x1, x2, and s as Fourier series and working from there. There's a bit more work to do because these non-polynomial nonlinearities sometimes cause problems, but there's ways for us to get around it. So take my word for it that we can indeed build a map out of this. But of course, that map will have that problem that I mentioned before, which is that it cannot successfully be used for a computer-assisted proof at the bifurcation points. So how do we fix this? So here's the trick. This trick has been used by, it's been used by a few people in a few different contexts. Sometimes it's called desingularization. Sometimes it's called blow up. And the idea is that we introduce another variable that will allow periodic orbits in the boundary to be separated from periodic orbits that limit into the boundary. And this is not going to it's not going to be intuitive as to why this works, but I'll try to explain it in a moment. The setup, if we're trying to prove a bifurcation that's, if we're trying to do the continuation close to the x1 equal to 0 plane, what we're going to do is we're going to introduce a new variable called alpha, which is going to behave like the amplitude of x1. So then we're going to find x1 to be equal alpha u, where u is another periodic function. And we are going to introduce the requirement that u at 0 is equal to 1. Now, why am I doing this? So we now go back to, probably like first year linear algebra. If we're introducing an extra variable and we want to be able to have solutions, we had better be introducing an extra equation as well. So we're introducing another variable alpha. We have to compensate for that by introducing another equation. And this other equation we're going to introduce is that u0 has to be equal to 1. And it turns out that this does work, and I'll explain why in a moment. But before getting to that, I just want to quickly mention that if x1 is not 0, so we're off of the plane, then this transformation is indeed uniquely defined. I can, I can just define alpha to be 1 over x1 at 0. And similarly, I can define u in terms of that. So it works fine. Now, on the other hand, if alpha is equal to 0, what happens? And it's a very, very simple proof, which I will show you in a second because it's inconsequential to the computer-assisted proof. In fact, we don't even need this, which is that if alpha is equal to 0, then in fact, there is a unique periodic orbit that would be living in the x1 equal to 0 plane, but in the variables u, x2, and s is isolated in a sense. The system of ODEs does indeed have a unique periodic orbit up to phase shifting that satisfies u of 0 equal to 1 and such that x2 and s is a periodic orbit in the x1 equal to 0 plane. And as for how we know that, so if we set alpha equal to 0, then this equation, this block right here disappears, and everything is and some things are decoupled. So x2 and s are now independent of u, and we know if we look at the x2 and s differential equations, this is simply the original ODEs restricted to the x1 equal to 0 plane. So in particular, we know that there is a periodic orbit in that plane, and we know from existing literature, and also we could check manually that in fact in this plane the orbit is exponentially stable. But since it's undergoing a bifurcation at this special parameter value of k, that means that the instability has to be in the u direction, or the x1 direction, which means that this function s over 10 plus s minus 0.8 has to have 0 average. Which means that if we now look at just the differential equation for u, it's linear in u, which means that, in fact, every solution is going to be periodic, and we can, in particular, just choose the solution that has u of 0 equals 1. So the main point is that this weird process of introducing an extra amplitude variable in some sense ensures that we have a unique solution a little bit away from the plane x1 equals 0, which persists as a unique solution in the plane x1 equals 0.
Kevin,
And Yes.
Is this blow up technique give you the tangent direction of a bifurcation branch?
It's not quite based on that. No.
Uh-huh. I see.
Yeah,
Okay.
it's a little bit different. I know
Thank
why
you.
you're asking, but yeah, it's a little bit it's not quite
Okay. Thank you.
yeah, it can't work for that special case that we still are having trouble with. Yeah.
Okay.
It's
Okay.
I
I
think
see.
it might be related. We could talk about that later. But
Okay.
yeah, it's a solution that works for this problem, but I don't know if it would work for that one. So, that's how this works here. And again, in terms of getting that proof of that theorem to work, I mean, it's partially done. It's just that we're trying to be efficient with it. So there's other applications of this desingularization trick in computer-assisted proofs. So I'll mention in particular the work of Elena Carollo, who is a collaborator of mine. She's currently at Technical University of Munich. She is, I think, for her PhD, she did a lot of work on continuation of periodic orbits through Hopf bifurcations using this idea, mostly focusing on ODEs. She and I worked on sort of two parameter continuation of periodic orbits in delay differential equations. Some applications to time delay SI model and a few other sort of classical equations and ODEs and delay differential equations. Um, and I'll also mention graduate student at McGill, Gabriel Duchesne. He and I, when I first started at McGill, applied these ideas to a global branch of periodic orbits in the Hutchinson equation with impulsive harvesting. So in this case, it's a non-smooth periodic orbit. There's like discontinuities. So we actually don't use Fourier there at all. We actually use a different setup. No Fourier analysis there. It's a little bit different. And just as a bit of an advertisement, once again, a lot of this has been made into a black box to a point. Elena Carollo, who again worked on that project that I mentioned with continuation of periodic orbits and delay differential equations. So she wrote most of this library that we developed in MATLAB. It's called Bivalve, mostly because we wanted to have a cool name, but it kind of made sense. Um, and So it is a essentially black box computer-assisted proofs library in MATLAB that can be used to prove periodic orbits, one-dimensional continuation or two-dimensional continuation of periodic orbits in ordinary and delayed differential equations, provided you have enough setup done at the beginning. So in particular, it only works for polynomial vector fields. So, the vector field I showed you before, the three-dimensional vector field, where there's non-polynomial nonlinearities, it can be handled using this library, but you need to do some work beforehand. The sort of nice thing about it, though, is that once the problem has been cast into the right shape, all those bounds like y and z needed for the computer-assisted proof, they're all done by the library. So if you think you have a problem that falls into the category of proving a periodic orbit in an ODE or a delay differential equation, and you want to maybe do that with a continuation, and if you want to do continuation or not do continuation, then send me or Elena an email and I'll tell you whether this library can do it. It is, however, in MATLAB, which is, proprietary software, and it costs money, and it requires an IntLab license, which also costs money. So, and it's MATLAB, which is an old language, so it's a bit slow. I mean, this, especially when we run this code to do two-dimensional continuation, it is absolutely a machine and eats computer memory so much. It's very, very. It eats a lot of memory to do it, but it is a black box, which is nice. So that's my last little advertisement. And before I finish, I'll just say that mathematics discovery is it's not a linear thing; it's a cycle. So maybe I don't know. Maybe some of you have seen now a couple of examples of what computer-assisted proofs can do, and maybe you're in the wonder phase. I myself am in the zealotry phase. Eventually, I'll get bored, but then maybe somebody will show me something really interesting, and I'll get excited again. And maybe that'll be one of you. So with that, I'll just say thank you so much for the invitation. Thank you for listening. Not every reference I mentioned in the presentation is listed here, but some of the sort of foundational ones, and also again my advertisement for Bivalve are here. If there's any other references that you would like me to give you information for, just send me an email. I'll link you to the paper, or um, Google keywords, whatever you'd like. So with that, thank you so much for listening, and should you have any questions, I will stay here until. Well, I've committed to staying here until 3 o'clock my local time. So,
Yeah.
thanks so much, and yeah,
Thank
thank you.
you. So Kevin, thank you for your very nice also preaching of the gospel of computer assisted proof, and also this by file, right? Do I
Yeah,
pronounce it correct? Oh, very nice.
yeah,
So
Bivalve, yeah, yeah.
by Valve, yeah. So questions, comments from the audience, just unmute your microphone and ask. I think this computer assisted proof is too new for us. Let me begin. So I am very interested in this blow up technique.
Right, yeah,
Yes. And because this transcritical bifurcation is a friend for us theoretics, because I mean we just prove it by bifurcation from simple eigenvalue. They are easy.
yeah, of
But
course,
it
yeah,
seems it's a challenge for you. That surprised me. And also, why don't you just use a theoretical result
right,
and then you move into the positive octane a little bit, and then you can
yeah,
use your computer assisted proof.
absolutely. That's a really good question. So there are a couple of reasons.
Uh,
First of so the first, and I absolutely agree with you. In fact, the first time I used this desingularization trick, it was with a student in McGill, and
yes.
I mean, I spent my PhD developing center manifold theory for impulsive delay differential equations, and in fact, there was a transcritical bifurcation of a periodic orbit, for which I, in fact, originally wanted to do exactly that. And it was actually a way easier problem because the transcritical bifurcation was not with another periodic orbit; it was actually with a steady state. So
Yes.
I could do all of the analysis right on paper.
Yes.
The problem is that if you want to know how far away in terms of parameters you can move to have persistence of the branch of periodic orbits, there are two problems with doing it using, for example, center manifold reduction. The first problem is that, okay, it's actually, there's a couple of problems. The first problem is that how far away you can move might be extremely small.
I see. Yeah. Yeah.
It could be that you can only move like 10 to the minus 5 or 10 to the minus 6 away before your analytical estimates break down. And it could be that the computer assisted proof in the regime where you're not at the bifurcation could still fail that when you're that close.
Mm-hmm.
So,
I
for
see. I
example,
see.
like it on a technical level, if you had a big enough computer, you can get arbitrarily close to the bifurcation. If you have a big enough computer, in that case, in this context, it means if you have enough memory that allows you to go to the level of numerical precision that will ensure that your the inverse of the derivative of your map, so that inverse of df at your approximate zero, is what will happen when you get really close to the bifurcation is that the norm of that operator is going to get huge. That's what's gonna cause problems. So, for example, very close to the bifurcation, it could be that your approximate zero is really good. Maybe it's 10 to the minus 16 ish because you're using standard double precision arithmetic. But when you're that close to the zero, the inverse of your derivative of your map could be like 10 to the 40,
Yes.
10 to the 60. And the
Yes.
closer you get, the larger it's going to get because, again, like the df is becoming singular, so its inverse is going to blow up. So you can get arbitrarily close. The problem is that you then have to work with higher precision so that your defect is actually lower than 10 to the minus 16. So that when you hit it with A, it's still going to be small enough to get a proof. So more precision then basically means you need more memory. The proof gets slower, and that's where the bottleneck is. So that's one reason. That's one reason that this is a little bit difficult.
I see.
The other reason that is that when you the other reason is that and it's a bit more technical and it's been a while since I did this, so I can't remember exactly why, but the other part is that you then need to, even if you use like a theoretical result to prove a small part of the branch of solutions near the bifurcation,
Yes.
it can be sometimes difficult to determine based on where that branch exists, how to know that this branch that you've proven to exist actually will connect with the branch that you're going to compute with the computer.
The
Proving
matching
the
problem, I would say.
yeah, the matching problem actually is a little bit subtle, and I spent a lot of trying to make it work, and it was it turned out to be much. It was a leaner and faster and easier proof to do with this singularization idea.
Yeah.
And then finally, and there's I guess one more reason. The final reason is that now I don't maybe there's an easy theoretical argument to do this with, but I don't actually know, and maybe you can answer. The periodic orbit that lives in the x1 equal to 0 plane, for example, um, is there an analytical proof that it always exists? And can you analytically do a center manifold reduction at the periodic orbit at the bifurcation point? That's the other thing, because if the periodic orbit itself isn't something you have your hands on, then how can you analytically determine a box in which you could then hope to connect the branch to something that I prove using a computer-assisted proof? Even the orbit itself in the plane is hard to get your hands on. So, yeah,
I see.
yeah, there's a lot of layers, and yeah.
I see. Thank you.
Welcome.
So, other questions, comments, remarks? Maybe let me ask a question. So, it's still about ODE, but now it's a traveling wave equation.
Yeah, right.
So,
okay.
traveling wave equation is an ODE on the real line.
Yes.
And it's not periodic solution.
Yeah.
It's this infinite unbounded real line give you a problem of finding the existence or even stability of traveling wave solutions.
So stability is a little bit more complicated, and I'll be honest, I have not done anything involving stability of traveling wave solutions.
It's a I don't know. It's a PD stability.
Yeah.
Sorry.
Oh yeah, I know. Yeah, we're talking about it's a PD stability problem. So like you maybe use an Evans function or something like this. Yeah. And I myself have not done anything involving computer assisted proofs of stability and traveling waves using Evans function, for example.
But how about existence?
Existence is something that we can do. So the standard setup that we use when we're trying to prove a connecting orbit, which is what a traveling wave is in an ODE. It's a connecting orbit between two steady states. So there is machinery to there's machinery to do computer-assisted proofs of parameterizations of unstable and stable manifolds in ODEs. And then you use that in conjunction with like a so-called rigorous integrator that allows you to, rigorously integrate from the boundary of your computed unstable manifold forward into the stable manifold of the other one. And then you bundle all of these pieces together into a single f of x equal to 0 problem. And you do Newton's method on it, like this.
I see.
Yeah.
Interesting.
Yeah. So yeah, we can do connecting orbits in ODEs, which means we can do yeah, traveling wave solutions of PDEs with without non-local effects. There is technically machinery to do connecting orbits in delay differential equations as well, but that is a lot more complicated. And while the machinery exists to do it, there are some subtleties that I don't think anybody's actually successfully used it yet. Mostly because the stable manifolds are infinite dimensional and they have some there are some technical difficulties with getting dimensions to match up when you define the f of x equals 0 problem.
I
But
see. I see.
but in principle, it can be done.
Yeah. Thank
Yeah.
you.
Okay.
Thank you. Very good. And questions, comments? I have plenty of questions, but instead you can stay here until 3.
Yeah, you've got me for
So
another
I
15
want to answer
minutes.
more.
Yeah.
Can you go back to your very beautiful cylinder of periodic solutions there? There are two pictures.
Yes. Yeah, here you go.
I mean, absolutely beautiful. Yes. And this one, because somehow some papers say these 3 ODE, they are chaotic region. In some invariant such that they are chaotic. But it seems like this kind of a cylinder is pretty stable, right? Do you know the basing of this periodic solution? Basing.
Do I know
the basing
sorry?
of attraction?
Oh, basin of attraction. Oh,
Because
yeah.
we have already done some numeric, it seems like the basing of attraction of each individual periodic solution is very big.
Okay. Huh.
Do you know
Yeah.
that?
I do not know. I haven't done much in the way of numerical simulations in the interior regime, mostly because so in terms of how how the student that's working on this
I see.
and I have our work shared. Basically, I'm handling the proof at the bifurcations, and he's handling the proof in the middle. And the way I start the proof is by so in the planes, the orbit is stable. So I basically compute an approximate guess by integrating forward and just grabbing data, transforming it, and working from there. And as for what he does, I believe he probably does the same thing, but near the boundary planes, it's stable, and there's a fairly large basin of attraction. I'm guessing I'm guessing where it gets weird is in the middle. And,
yes, sure.
And so yeah, neither of us would have actually looked at the dynamics in that intermediate regime because our continuation would have been seeded with data that starts at the edges.
I see.
So yeah, so I don't know what happens in the middle.
But then each periodic solution you obtain is stable or not? Do you know that?
I do not know. I mean, we could compute Floquet multipliers along the branch to see what happens. Absolutely, we could. But yeah, that's just another calculation to do.
I see. Yeah. I see. I want to make a comment here. I am so interested in the minima period along the continuation because if the minima period along the continuation is bounded, like this picture, bounded, then I can use a global Hopf index to prove the existence of a continuation easily.
Okay. Yeah.
But the main difficulty is, of course, to prove the minima period is bounded. And you show me this picture, amazing to me, really.
Yeah. So I mean, that is one nice consequence of the way we set up the computer-assisted proof. We solve for the period, so we can determine global bounds on the period over the entire branch. So
do you have the formula or some implicit formula of the time map?
Of the time map? Sorry, which map?
Time map. Time map. TIME time map. To know the relation between time and the position of the solution. The time map.
Time and position of
so
solution.
for example, how do you draw this picture, this KT picture?
Oh, right. So I mean, in this specific case, I believe so. This was prepared by Olivier. I would guess what he did is that so in this case, it's probably just an interpolation of a few discrete points along the branch.
I see.
Yeah,
I see.
yeah. So I mean, what we can't do from a computer-assisted proof like this is, for example, there's no way to construct an analytical representation of the period
Okay.
map. Yeah. Yeah. The best we could do would be to, for example, say that between k equals, for example, k equals 100 and k equals 110, the period is strictly between 2 points, two numbers, and we could, for example, prove that the period is monotonically decreasing.
Wow,
Like that's
amazing.
yeah, yeah. So we can prove monotonicity of the period for sure if we wanted to.
Even this is amazing, I would say. Yeah. Okay.
Yeah.
Very good. Very good.
Yeah.
So, any further question, comments? Okay. If this is not the case, then let's thank the speaker, Dr. Kevin again. Kevin again. And
Thank you,
thank
everyone.
you again. Now it's almost 3 a.m.
Yeah, I guess it is. I should probably go to bed. Getting up in about 5 hours to go to work. But yeah, it's been really nice talking with all you. Thank you.
Thank you. And I will share your talk to Nicola, Filippo, and other friends. Okay. And also
Yes.
in the NCTS, but you want to make it private or public? Private, right? Or
Oh, it doesn't matter. It can be public. It
okay,
doesn't.
okay.
Whatever you
Then
like.
people
Yeah.
can see your gospel or computer assisted proof. Really,
Yeah, that sounds great. Yeah.
very nice. Thank you. Okay, so I will
Thank
write
you.
an email to you afterwards about our progress. Okay.
Yeah. I'll give you some more details.
Yeah. Okay. So best wishes and keep in touch. Okay.
Yes, absolutely.
So have a good night. Bye bye.
Thank you. You too. Bye-bye now.